Okay, good afternoon, everybody. Thank you for joining this afternoon session after lunch. And we will start this first session of this afternoon and resume the lecture about gravitational waves from phase transition. Thomas will do that. Please start.
Okay, so this will be the start of the third lecture. So the third lecture will be split into two parts. And this time not on the blackboard, but I will present slides. So far less equations, more pictures. So this will be relatively lightweight. I think it's just the right thing after lunch. And the outline is roughly the following. In the first I will give an introduction. I neglected a little bit the motivation of the whole business and also the context. So I will fill this in and also try to remind you what we learned in the first two lectures. Then in the second part, I talk about recent results in this business, namely considering simulations. And then tomorrow, I will cover PTAs, in particular NANO-Grav, and how one can potentially distinguish such a gravitational wave source from something astrophysical. All right, so I guess most people have seen this plot before. This is supposed to be our universe. So we start in the Big Bang, and then we have a hot phase after reheating, and then the universe expands and cools down. And depending on the time, there are different temperatures, and at different temperatures, you have different phenomenology and different kind of physics is relevant, right? And time is flowing to the right, and since the universe is cooling, temperature is increasing to the left, right? And this is what we learn, but actually, I think it's not the right picture. I think what the picture is actually this one. So what we do is we observe the universe today, right? And then we know how physics works, and then we use this knowledge, and then we calculate backwards, right? So basically, we know what happened when the CMB was generated because of the observations today, and we know how atomic physics works, right? And this is interesting because this gives you a link between cosmology and particle physics. Okay, so first example here would be what I just said. It's a CMB. So we know how atomic physics works, and because we know how atomic physics works, we can make a prediction about the CMB, and along the way, we can learn something about cosmology, right? So there's a strong link here between what we know from the lab and what cosmology is telling us, and this is what we want to employ. Second important example is, of course, BBN. So we know how nuclear physics works. This is at temperatures of MeV scales, which is tightly linked to the PTA signal, right? And we also know the light abundance of the elements in the universe, and we know the abundance of the light elements because we have a few inputs from cosmology, like the baryon yield, and because we know how nuclear physics works, right? There's also another important lesson here. We can, of course, measure these light abundances, and because light abundances agree with what we expect from BBN, from this calculation, we know that the universe must have been in this hot state, right? So we know that after inflation, after reheating, the temperature of the universe must have been higher than this MeV scale, because otherwise the light abundances would not be the ones predicted by BN, right? So now the idea is to push this concept once further, right? So currently at LHC, we test the electric sector. So we found the Higgs, right? We try to understand how the standard model works at electric energy scales. And now we would like to make some connection to cosmology and see if the universe really was reheated to these electric scales by identifying some relic from this era, right? And of course, what we're interested in here are gravitational waves. And in this context, it might be that there are gravitational waves from the phase transition, which is connected to the electric symmetry breaking. And once we identified really a gravitational wave source from the phase transition, we know that the reheating temperature must have been higher than electric. Right? So the main idea behind this whole field is basically to try to establish another link between particle physics in the lab and cosmology at higher temperatures, namely electric temperatures. In principle, there are two links. They're not just gravitational waves. There's also a link via baryogenesis. So you know that there's an asymmetry between baryons and antibaryons in the universe. And baryogenesis is a mechanism to explain this. And one of these baryogenesis mechanisms operates also at the electric scale, right? So if we could pin down that really electric baryogenesis is responsible for the asymmetry by, for example, measuring EDMs or something else, then we also would know that the temperature of the universe was at these high scales initially. Okay, so how does electric symmetry breaking work? I had a similar plot at the blackboard 2 days ago. So at electric scales, you would consider the Higgs field. So you have this Mexican hand potential, which is designed to break the electric symmetry. So you have the Higgs field, which cannot sit in the symmetric situation here, but has to sit in non-symmetric in a broken phase where the Higgs has a VEV. Right? But we also know that if you add temperature corrections to this kind of potential, then actually the only minimum of the potential becomes symmetric, and at large temperatures, the symmetry must be restored. So for example, in a famous paper by Weinberg, he calculated that the lowest order, there's this mean field contribution, which is just h squared t squared. This will make this minimum, this maximum a minimum at large temperatures, because this coefficient here is positive. So now the question is how we come from this picture to this picture. And in principle, there are several possibilities. So there's one boring possibility, and that is basically when this happens rather slowly, and the field basically slowly grows out of the symmetric phase and moves slowly towards the broken phase. So in this case, you would have a crossover or a second order phase transition. There's also the other possibility that we discussed, namely that you have the coexistence of the broken and the symmetric phase separated by a barrier. And in this case, the field has to overcome this barrier by either tunneling or thermal fluctuations. And in this case, you would have a first order phase transition, which proceeds by bubble nucleation. So to us, the right-hand side is the interesting case. So we don't consider this one, because this would not lead to any interesting dielectric stars, in particular no gravitational waves. Okay, so what's the status in the standard model? I mean, we found the Higgs, right? So this potential is really what we know. By now we know what the VEV is. We also know what the coupling is from the Higgs mass, right? So the question is, what is this phase transition in the standard model? And unfortunately, it turns out in the standard model, there's just a crossover. There's not a first order phase transition. So this is known from lattice studies in the 90s. And at the time, the Higgs mass was not known. But the conclusion was that if the Higgs is heavier than the W, then there's no first order phase transition, right? And by now we know the Higgs mass is 120 something, which means there's no phase transition. In the standard model, it's a crossover. But of course, we just started to explore the electric sector. There could be other scalars, there could be more particles, and there could be SUSY, right? And depending on how this extension looks like, it's relatively easy to get a first order phase transition. So one of my favorite examples is just the standard model with a singlet. So now you have a potential which depends on two scalars, depends on the Higgs VEV and also on a scalar VEV. So your Higgs potential becomes two-dimensional, so there's a Higgs direction in a scalar direction. And even if you impose a Z2 symmetry and only have a handful of operators, so there's just S squared, S to the 4, and S squared, H squared, in addition to the standard model, you can already construct a potential which at 0 temperature has two minima, right? So it's really, really easy to construct a potential without any tuning, so all the numbers are really natural, in which the electric phase transition actually will be really, really, really strong, because there will be a large barrier between the two local minima already at 0 temperature. Often in this model, this is what people call a flip-flop model, because often the phase transition happens first in the S direction, and then the strong phase transition is the second one when the S loses its VEV and the Higgs gets its VEV. So this resembles basically the twin Higgs model that we've seen 2 days ago. Typically, the second phase transition would be the one which is strong, where the electric symmetry is broken. So in the second phase transition, you can have also baryogenesis, because in the first phase transition, you don't break electric symmetry. And also in the second phase transition, you would have the gravitational wave production. All right, so in one of the lectures, I mentioned that kind of the main example for first order phase transitions is boiling water, where you have water and you heat it up, and then you get these bubbles of gas. But in the cosmological context, this is actually not the right analogy. So a better analogy in cosmology is chemical combustion. So imagine you have just an inflammable gas, right? And then you ignite the gas somewhere in space, and then you get a fireball, right? So a lot of energy is released, and this is the energy we would like to use to produce gravitational waves. Also, the wall velocity here is not microscopic, it's macroscopic, so it's of order of the speed of light, right? So these bubbles are really, really fast and carry a lot of energy. And that's what we want to use. All All right, so the picture is we have this phase transition, we have these bubbles. These bubbles carry a lot of energy. As long as you don't have just isolated bubbles, nothing will happen because of spherical symmetry. But once these bubbles start colliding, then gravitational waves will be produced. And this will be a stochastic gravitational wave because many of these bubbles will contribute nowadays, right? So you can think like in the CMB, where you see many horizons when the CMB was produced. I mean, this would be at even earlier times. So you see even more horizons, so the sky would be made up from trillions of patches of these colliding bubbles, and these would produce a stochastic gravitational wave background. All right, however, this is not a really easy process, because during this process, during this phase transition, there's different sources of gravitational waves. So the first one would be the collision of the scalar field configurations or the initial fluid shells. This is something what we wanted to capture by this envelope approximation, right? Then there are sound waves, because the bubbles push around the plasma, what you've seen in lecture 2. There are long-lasting sound waves in the plasma, and also these sound waves will produce gravitational waves. Because these sound waves are long-lasting, it's believed that these are actually the dominant source of gravitational waves. On top of it, there might be additional effects like turbulence, also the production of magnetic fields, and especially the last point is barely explored nowadays. So in the beginning, people did a lot of analytic studies or some relatively simple simulations of these collisions, but in the last 10 years, simulations became the main tool to incorporate most of these effects and get a really accurate result and a really precise prediction for this phenomenon. All right, so this leads me to the second part, to these simulations. And what you can see here is one of these early simulations. So the early simulations were done by a group in Sussex and in Finland, in Helsinki. And here you can see these bubbles expanding. You can also see these shaded regions. So that's basically the region where the fluid is pushed around. So what you see here is the total energy of the system, right? And then when these bubbles collide, there's more kinetic energy deposited in the collision regions, and exactly these regions will produce gravitational waves. And even at late times, when the phase transition already completed, there's still a lot of motion in the plasma from these sound waves. Okay, so just to remind you, what are the important parameters, what are the scales, and I want to just quickly review again this back on the envelope calculation. So one important scale here is the temperature, but we've seen the only point where the temperature enters is actually from the redshifting, right? So you produce some gravitational waves during the phase transition, and then the temperature will tell you how much this gravitational wave spectrum is redshifted to lower frequencies. Then another important parameter is the parameter beta. So this parameterizes the duration of the phase transition. So the probability, nucleation probability, is exponentially increasing, and we parameterize this by this parameter beta. And typically, this parameter beta is linked to the Hubble scale. This parameter beta is also linked to the bubble size, right? Since typically you have hundreds or thousands of bubbles. This means that the mean separation is linked to beta, so it's roughly 3 over beta. And of course, also the wall velocity will enter here, okay? And then the final parameter that we need to know is how much latency.
May I ask one thing?
Sure.
Do you have any clear idea of what parameter it gives us some critical impact for the beta divided by h? By controlling which parameter of the Lagrangian or your potential?
Which parameter is controlled how in the potential, you mean?
Yes, in order to enlarge the values, make it small. Right.
Well, I can tell you in terms of classes, no? So in the in the old calculation of the standard model, so what I'm plotting here is the tunneling action as a function of the temperature, and there's a critical temperature, and there's 0. Okay, so the tunnel action blows up here, right? And then in many models, at some point the barrier vanishes, and this leads to the fact that beta, which is the slope here, is relatively large, right? On the other hand, if the barrier persists, it looks like this, and then it might be that the beta is actually small. Also, I didn't mention it yet, but there's of course alpha, right? And typically when when you tunnel here or here, then alpha is also larger because alpha scales basically like the latent heat divided by T to the 4, right? And here the nucleation temperature is much smaller than the critical temperature. So, and this is a sizable effect, right? So if the nucleation temperature is half the critical temperature, you gain a factor of 16 here, right? Because it's T to the 4. So in this kind of class of model, which would be the singlet extension, right? You typically get a relatively small beta, right? And a large alpha. But in models like the standard model, where the barrier is coming from the cubic term, typically you get beta, which is between 100 and 1,000, and alpha, which is like 10 to the minus 2.
Yeah, then if I clarified my question a little more, then how do you control the action? I mean, which parameter has a crucial impact on the size of action?
Yeah, well, this depends a little bit, of course, on the model you're choosing, right? But for example, if you take the singlet,
yeah, right. I mean, for example, here.
Okay, so consider this potential. So it's V of H and S. One relatively suggestive way of writing this action, you can write it in the following way. Okay, so this guy contains a term which is H squared, S squared, H to the 4, S to the 4, and H squared, S squared, right? But in principle, what this looks like is like a super Mexican hat, right? So if you would just plot this potential in the H and S direction, then there would be a flat direction, right? Okay, so now you can basically employ this term in order to lift the barrier between these two minima. So kind of this guy controls the height of the barrier, right? And if you make this large, then basically this guy moves up. So if you move this guy down, so there's this critical value 140, then phase transition would be here, right? If you move this guy up, then at some point it will happen here, and beta will become smaller and alpha larger. So in order to get alpha order 1, in this kind of model, this would involve a little bit of tuning in this parameter, right? Which is a little bit nasty because the H squared S squared is basically a combination of this guy and this guy.
Thermal impact is also important, right? The coupling, the strength of the coupling to thermal bath.
Why? Which coupling?
I mean, in order to have, for example, first order phase transition, not only the shape of potential, but also you have to include the thermal effect too, right?
Yeah, but
including all of them.
But in principle, this is not so critical. So let's say you would do mean field, right? Then there's a kind of a term which goes like H squared T squared, and there's a term which goes like S squared T squared. And then there's a coefficient here and a coefficient there, right? So in principle, what you have to make sure is that, now I have to think, that this guy is smaller than this guy in order to end up in the electroweak phase at small temperatures, right? But otherwise, they depend, and I mean, these guys are typically, so it's the sum over all your cover couplings divided by 24 or something, right? So typically, this is not small anyway, right?
Okay.
So there's nothing crazy going on. So there's no tuning in here. These are just generic numbers. So the only tuning you have to do in principle is to make this happen. So there's kind of a coincidence between to get this term, and then this has to be not too large in order, because otherwise you get, if it's too large, you get stuck, right? But there's no tuning. All the numbers basically look natural when you write down the potential.
Okay, thank you.
All right, okay. So, right, so besides the wall velocity, which of course enters in the dynamics, there's also this strength of the parameter, which we discussed mainly last time, which is roughly speaking the ratio between the latent heat and the total energy, because the latent heat is ultimately what produces the kinetic energy, which drives the gravitational wave production. Okay, so, and again, in order to calculate what would be the peak today, you just calculate the frequency at production, which is 1 over R star, which goes like beta, which is roughly 100 times H. You know that H scales like T squared. You know how to redshift, and what you get is this equation. So for natural beta values of 100 over H, and the temperature close to the electric scale, you get millihertz, which is in the LISA band. On top of it, you know how the gravitational waves redshift, and that's this 10 to the minus 5 I mentioned last time already. So the gravitational waves are suppressed by this latent heat, the strength alpha squared, and this 10 to the minus 5, and this h over beta squared we had at the blackboard last time. Okay, just to show you the landscape of the different experiments and what we can expect. So here you see the different frequencies. On the left is Planck, so CMB measurements, and this is PTA, space-based missions like LISA or BBO, LIGO, and then eventually here there will be new experiments at some point. So people work on cavity experiments, for example, but it's unlikely that the cavity experiments will be actually competitive in terms of omega. Then in terms of sources, there are different sources. There is the one from inflation. It's this tensor to scalar ratio we discussed this morning. Then there might be a contribution from strings, like we discussed in the nice talk yesterday. Then there are contributions from inflation, like from the thermal plasma at an early stage, or from preheating. And because this happens at really large energy scales, correspondingly the frequencies will be really high. And then in red, what we are actually concerned about, the first order phase transitions. And as I told you, if the temperatures are 100 GeV, the frequencies are millihertz, which means that the signal would be in the LISA band. But of course, this temperature is a really important input here. So you could also imagine that there's a phase transition in the dark sector at around QCD temperatures, and then the phase transition would be in the PTA band.
What happens to the background equation of state during phase transition?
To the what?
During a first order phase transition, what happens to the background equation of state? Do you follow a bit?
Well, this depends a little bit, no? So one way to see this is you can calculate the CS squared doing the phase transition, right? And then and then in the electric case, actually, it's almost radiation all the way. But if you do it in QCD, because the number of degrees of freedom in QCD changes a lot, I think there's a dip, right? But then I think it's a dip, and then it goes up to because you're kind of matter-dominated, no?
There are small dips for electroweak as well as electron-positron annihilation. But in case of first order phase transition, so QCD is a crossover. So I understand that the dip is low.
Right.
But now you're proposing that there may be a first order phase transition at electroweak.
Right.
What would happen to the background equation of state?
Yeah, I think at the electric scales, you're always dominated by radiation anyway. So I think, I mean, something might happen, but you will stay really close to 1/3. The only thing that can happen, and that's also something which was mentioned at some point, is you have these supercooled phase transitions. For example, if your model is nearly conformal, and you have a lot of supercooling, then in principle, you enter a regime where you might be dominated by the CC, but at the same time, the speed of sound of the fluid is still 1/3, right? So in some sense, the cosmology changes, but the speed of sound stays the same. Yeah.
The reason equation of state remains radiation dominated is because your bubbles are relativistic.
No, because basically the speed of sound is just the dp, de of your fluid, right? And the CC doesn't enter here, right?
But in the fluid, you are having a phase transition. So part of the fluid, T mu nu, is contributed by bubbles, expanding bubbles.
But this is just a surface effect, right? I mean, of course, you could calculate if the surface of the bubbles contributes something there, because the equation of state there will be for sure different. But it's just a small fraction of the total volume. No?
It's also an interacting fluid. So
so I think there would be a penalty factor from the fact that it's just a surface effect. No? Okay, but there's also another exciting effect here. For example, if you consider a phase transition in the LIGO band, you can in principle test thousands of TeV. And this is, of course, an energy scale that you will never be able to test in a collider, right? So this kind of experiment has a huge reach in terms of energies if you're interested in particle physics. So for example, if there's a gut phase transition or something, that's something you might pick up in high frequency experiments. Okay, so what I'm gonna mention next time, so this is the old NANO-Grav data, the 12.5-year data, which you can, if you know the data, you know this because the omega is sloping down. So one of the games which was played a lot since NANO-Grav released the data was, of course, to try to explain the tentative signal in NANO-Grav with a signal from a phase transition. And there you can play different games. For example, if you have a supercooled phase transition, you could argue that the main contribution comes from bubble wall collisions. And then the spectrum looks a little bit different than when it comes from sound waves. And that's why people kind of favored super good phase transitions to explain the NANO-Grav 12.5 years. But of course, I guess you know that by now the spectrum is actually sloping up. So this means that nowadays people will try to explain the signal with the infrared tail of the spectrum. But I will discuss this in a little bit more detail next time. All right, so far so good with the introduction. Let me now move to this kind of open question from last time, namely this, what I call geometric factor, which is kind of this order 1 factor that you have to determine from simulations. Okay, so there was one, this is kind of conventional or traditional approach, which was pushed by the Sussex Helsinki group. And what they do is they study a fluid with 2 components. So there's a usual fluid, which is radiation. So that's the energy momentum tensor of a perfect fluid that we discussed last time, and they just consider radiation. And then there's a second component here, which is the scalar field, namely the Higgs. And the energy momentum tensor of the Higgs has a kinetic component and also the potential component. And then the equations they solve is total energy momentum conservation. This equation here, and on top they solve the Klein-Gordon equation. So in the Klein-Gordon equation, they have to add one phenomenological term, and that's a friction term. I told you that in order to determine the wall velocity, that's a really tricky business. You have to solve Boltzmann's equation. This is really a mess. And in order, of course, you cannot solve the Boltzmann equation in this kind of setup. So what people do is they just add one term to the Klein-Gordon equation, which is a friction term. So this will stop the wall from expanding. Okay. And basically, you have one free parameter here, this eta, this friction parameter, and you can choose this friction parameter such that you attain the wall velocity that you want, right? So if you want to do a simulation at 0.5 the speed of light, you would look for an eta such that in the plasma, the scalar field really expands with this velocity.
Excuse me?
Yeah.
May I ask? So since you are adding a dissipative term, sort of,
yeah,
wouldn't you also have fluctuations? Can you have dissipation without no fluctuations?
You mean fluctuations in the fluid from the...
For the scalar?
Well, I mean, this is kind of what happens, no? So the scalar field, driven by the latent heat, will try to expand, right? And then the friction term will stop it by basically transferring energy from the scalar sector into the fluid sector, right? So if you write down now the Navier-Stokes equations, there will be a source term from the scalar field in the Navier-Stokes. But all of this happens, of course, there's this hydrodynamic effect, which we studied last time. But close to the wall, there will be also an effect where the fluid is kind of locally driven out of equilibrium or not out of equilibrium, but away from the background by the scalar field. Yeah. So in this sense, it's fluctuations, right? But it's not that these are really fluctuations everywhere. They're relatively small scale because the scale of the scalar field is really small. And it only happens close to the bubble walls. So again, there's a penalty factor by a surface. No? Okay, so and then they basically, what they do is they first generate a history of bubbles. So they kind of randomly choose bubble times and bubble locations where the bubbles are generated. And then put a bubble which is large enough that the bubble will start expanding. And then they track the system and study how the scalar field evolves and deposits energy in the fluid. Right? And then they just follow this dynamics. And ultimately, they can just extract the energy momentum tensor of the fluid. And then they put the energy momentum tensor in this Weinberg equation, which I presented, to get the spectrum of the gravitational waves. This would be kind of a result of such a calculation. So they identified that the peak of the power spectrum would be somewhere here. There's a tail, and well, in the infrared, they cannot say much because essentially there are not enough bubbles in the simulation. Okay, so in principle, I think if you just want to determine the amplitude and the position of the peak, this is a really robust procedure, right? There's not much physical input, and I would say this was really a big step forward because they realized the importance of the sound waves. At the same time, it's a really costly procedure. So these first simulations were done on a huge cluster, so thousands of cores, right? And the simulation took, I don't know, months, order of magnitude, right? So it took a long time, and it's really costly. Okay. So, so at the time, this was, of course, a big step forward, but it's always a little bit, if there's only one group doing simulations, right, and there's no cross-check, that's always a little bit, yeah, not so good. So at the time, we wanted to check this result, but we are not computer guys, right? So we didn't want to run a cluster. So we wanted to come up with a procedure which is a little bit more lightweight and actually produce a similar results in kind of a simplified framework. So, before I explain what we did, let me explain the problem. So the problem here is that in principle, there are 3 different physical scales. So the first physical scale is the wall thickness. That's a scale on which the Higgs goes from a 0 value to a finite value. And this scale is tiny. So in a physical system, this wall thickness is roughly of order of the inverse Higgs mass, right? And the Higgs mass is something like 100 GeV, right? On the other hand, there are 2 macroscopic scales here. The first one is the bubble size, right? And then there's the thickness of this shell where the fluid is pushed around. So in this picture, the shell thickness would be this one, and the bubble would be from the wall to 0, right? So this is 0.5, so 0 would be here. So there's a bubble size, there's a shell thickness, and then there's a tiny wall thickness. And what you have to do is you have to resolve in the simulation all the 3 different scales, right? But these scales, so the wall thickness scale and the bubble size are 16 orders apart. So clearly you cannot resolve this in a computer. So what you do is you choose parameters such that you can resolve it, right? So in particular, you choose a tiny Higgs mass such that the wall thickness becomes somewhat smaller than the shell thickness, and the shell thickness somewhat smaller than the bubble size. Okay? And then you take these 3 scales and you have to basically squeeze them between the grid spacing because you want to resolve. So if you have the Higgs wall, so the Higgs goes from 0 to some finite value, right? And basically you want to resolve how the Higgs field does it because this is giving you the latent heat. Right? So this would be the grid spacing, and with the grid spacing, you want to resolve the change in the Higgs field. Then you have the macroscopic scales, and you want to have, let's say, 100 bubbles in your simulation, which means that the box size is sizably larger than the bubble radius. Right? So this means you have 3 scales, which you have to squeeze into these grid spacing and box size, which means that typically you have to do a simulation with, I don't know, 4,000 grid points in order to get a reasonable result. Okay. So if you're a particle physicist and you want to simplify your life, you say, okay, I'm going to construct an effective field theory, right? EFT. And in an EFT, what you do is you integrate out the highest energy scale. So what's the highest energy scale here? Well, it's the smallest length scale, which means it's a bubble thickness, right? So our idea was now to kind of integrate out the Higgs. So we make the Higgs non-dynamical in order to get rid of one of these scales and make our life simpler in simulations. And that's exactly what we did. So how we do this? Well, our equation of motion is just hydrodynamics, so we just have the fluid. And the Higgs field is not dynamical, but it's still encoded in the equation of state, right? So last time we had this back equation of state, which changes from this epsilon is 0 in the symmetric phase, or the other way around. It's non-zero in the symmetric phase, and then 0 in the broken phase. And what we do is we kind of make up a bubble history. So we kind of randomly chose at which time and in which location the bubbles are nucleated. We choose the wall velocity as a free parameter, and then we can calculate epsilon. So every time at a specific, so we choose a specific time, and then every time you are inside a bubble, we choose this epsilon value, which is 0, and if you are outside, then we choose an epsilon value which is positive. Right? So this means that our epsilon is now basically a space and time dependent function, because we know where the bubbles are at every point in time. And this changes the equation of state of the fluid, right? And because of it, we hope that this equation will lead to the same fluid dynamics as before. Okay? And of course, we now gained in the sense that we don't have to resolve the bubble wall, so this problem goes away, right? But we got a different problem, and that's that we have now to deal with kinks, right? So even though we got rid of the Higgs, right, we know that in the physical solution, the fluid velocity has to drop at the bubble, for example, for a detonation, right? So we know that the fluid solutions that we're looking for actually are not continuous, so there are these discontinuities in our fluid motion. So this means that we need kind of a numerical framework which can resolve shocks. Okay, so just to give you a rough idea, so this is an old standing problem. To give you a rough idea what happens here is the following. So imagine a differential equation which is just a right mover. So dt plus dx acting on f of t and x is equal to 0. So everybody can write down the solution to this problem because you know that f is just g as a function of x minus t, right? It's just a full-fledged solution. So if you now choose a step as initial condition, you know that the solution is basically a step moving to the right, okay? But if you discretize this equation and try to solve it, you will encounter at least one problem. One problem is too much viscosity or damping. In this case, the step will not stay a step. It will be washed out and become really broad. Okay. There's also the opposite problem. So if you make your method a little bit more sophisticated and achieve less viscosity, typically you find something which is called Gibbs oscillations. And this means that close to the gap, actually there are oscillation features. And this is, yeah, I mean, people studied this to death, and they concluded that if you have a linear differential equation like this, and you solve it numerically, you cannot avoid both problems. So there's a trade-off. So either you get this problem or you get this problem. And the solution to the problem is to make the equation nonlinear. So you start with a linear differential equation, and then you basically add small nonlinearities in order, in the hope that you can avoid both problems. So we were looking in the literature for there are all kinds of different schemes that try to achieve this, and there was one scheme which was yeah, especially appealing to us, which is called Koganov-Tetmore. So this is tailor-made for hydrodynamics, and it's really quick. So this is, I mean, implementing the scheme is not really hard. Understanding what the scheme does is considerably harder. So just to flash a couple of points, what's going on. So you try to do something which is called total variation diminishing. Then there's something called hybridization, which is making the linear equation nonlinear. And there are more concepts like yeah, min-max limiter and so on. So there's a huge literature behind this, but it's a widely used scheme, and it's exactly what we needed in our context. Okay, so we implemented the scheme, and as a first test, of course, what you do is you just put a single bubble and see if the single bubble approaches the self-similar solution that you know from the calculation from last time. So what you see here is we put a single bubble in the box and let the bubble expand and see what the fluid is doing. And in the beginning, you can even see the grid points, right? So the bubble is basically covered by just a few grid points, and then the bubble expands. And as soon as the bubble is covered by, I don't know, like 20, 30 grid points, the fluid which is established around the wall is exactly the self-similar solution from the spherical symmetric calculation that we did last time. So once you see this picture, and we also did, of course, not just, this is a detonation, we also did this with deflagrations and hybrids of different strengths. And we always found that the convergence, as long as the profile is not too thin, that the convergence to the self-similar solution is really, really good. And this is good news because it tells you that the kinetic energy in the plasma is exactly the one that you expect. And this means that this scheme kind of works. So what did we gain? Well, instead of a simulation with like 4,000 cubed grid points, we can now do a simulation with like 500 cubed grid points, right? And this is a simplification by roughly a factor 2,000, which means instead of waiting a couple of months on a cluster, you basically can take one node and do the calculation overnight. So it's basically a huge, huge improvement. Okay, so at this stage, I wanted to show you a simulation. I see we had far too many questions. Okay, So what you see here is 3 panels, and the 3 panels show the velocity, the enthalpy, and the vorticity. And this is basically the point where the first bubble nucleates. And then it takes a relatively long time until the second bubble shows up, right? But then after the second bubble showed up, it goes relatively quick, so more and more bubbles show up, and then exponentially many bubbles are nucleated. Right? So at this point, you see that there's already quite a bit of kinetic energy, even though the phase transition is not yet completed. And there's also, at the surface, clearly the vorticity is kind of an artifact from the simulation. But you see that also inside the bubble, some vorticity is generated. Okay. And at this stage, basically the phase transition is completed, right? But still there's a lot of kinetic energy coming from the sound waves. Okay. So I had another like 20 slides, I think, but let me just wrap up. Okay, so the next step is, of course, to extract the spectrum. And one new feature we found is that there are now 2 features in the spectrum. There's not just a peak, but there's also a knee. And it turns out that the knee is from the bubble size, while the peak is actually not from the size of the bubbles, but from the shell thickness. So it's a smaller scale, so it's higher momentum, right? And it turns out the peak is actually from the shell thickness, not from the bubble size. And of course, you can study this systematically by just choosing different wall velocities, making the shell, the sound shell thicker or thinner, and then extracting the parameters. And since everything goes relatively quick, you can do hundreds of simulations and really study all these things in detail. So the conclusions would be that at this stage, at least for this kind of strength, which is not super large yet, we have very accurate predictions, which are really reliable and really high precision gravitational wave spectra from the cosmological phase transition. So if you have a favorite model and you think there are gravitational waves, what you have to do is you have to calculate these parameters, alpha, beta, v, and t, and then you can basically use our results and expose them to an experiment like IISER or PTA. Okay, the next part I wanted to talk about the new results where we venture into the strong regime where we have now phase transitions which are 0.5, and there are some new interesting features like a decay of energy and some vorticity. So we believe that this is basically the first time that we've seen turbulence in these simulations. So we have to check this in a little bit more detail, if this is really turbulence and has the right properties, but it looks really promising, and this would be basically the next big step to try to establish how turbulence works in this kind of context. There are a couple of other open questions, but these are, more like technical details for the aficionados. And with that, I would like to conclude, and thank you.
Okay, the session is open for question now.
Yeah, I have a question about the modeling of the friction term, right, for the simulations, because from the full simulations, also with the scalar field, one of the points is that you treat your friction parameter in a way that you reach a particular wall velocity. But then when you're doing that, that's kind of, that part is what the Higgs simulation can deal with on a way, right? So, well, I mean, you put that by hand, right? So, but the moment that there's a big difference maybe between the Higgs and the full simulations is when you start having collisions, and then there might be some effects there. But at the same time, that's when maybe this modeling actually becomes more relevant, right? So
on one hand side, I agree that most of these effects would be captured by the collisions and not by the sound waves. So the long time behavior should be similar, which means if the source is acting long time, then these differences would not make a big difference. Another point I would like to make is that, of course, in these simulations, eta is just a number, right? And this is not what you would get from Boltzmann equations anyway. I mean, if you solve Boltzmann's equations, you have effects away from the wall, and the dynamics is really different. But even if you would go to the local approximation, where this would be your friction term, eta would have a phi and a t dependence, right? And I think this dependence would also exactly change these effects that you mentioned. So yeah, I would say in terms of these effects, we are different, but I would also claim that the effects that they see are not really the physical ones, because you would need to include this dependence in order to capture really the physical response.
Any other question?
So when you are integrating out the Higgs, so the effects are, if I just to make sure, so one is VW, and other one is the width of the wall.
Right.
Okay. So can you explain a bit on the width of the wall? Like
Right. So I mean, let's say you would really solve the equations that they solve numerically, like these guys. Then in the Klein-Gordon equation, this guy spits out, roughly speaking, the mass, right? So basically, what you expect to get is roughly like a Tanz shape, where the thickness of the wall is given by 1 over m, right? And this is 100 GeV, while h squared is 100 GeV, sorry, to the 4 divided by Planck mass squared, right? So basically, this guy and the bubble size, they are 16 orders apart, right? So what they do is they choose a Higgs mass such that this guy is relatively large, and then they extrapolate. I mean, they do only one simulation, right? But the idea is to extrapolate to the physical point, or they hope that the Higgs thickness does not make a huge difference. I mean, also this is debatable. Also, the impact of this term is, of course, debatable compared to what the Boltzmann equation does, as we just mentioned. So yeah, but yeah, so this is basically the requirement. But in any case, even if you choose this thickness to be really, really large, it's a different scale that you have to represent in your lattice, right? So if you have your fluid, then you have to make sure that this is bigger than the scale on which the Higgs mass is changing, right? And the grid spacing is even smaller than that. And basically what we got rid of was this one scale. So our grid points would be basically just representing the fluid shell, and that's it. Yeah.
Okay.
So, the first bubble is nucleated, and after a while, after a while, the secondary bubble starts nucleating. So, is the nucleation rate is the equation that is governing that inside, or like how do you determine in the simulation that after how long after the first bubble the secondary bubbles
well,
are?
in principle, you can just sample, right? You say the probability is e to the beta t, right? And then you just, I mean, you do this beforehand, right? So,
okay,
so this is not in the
ah.
simulation. Basically, you do a simulation with small delta t, you check what is the probability, you generate a random number. And actually, there's an even smarter way of doing it that we that we explain in the paper, by going to a different time variable where the distribution will be uniform in time, and then you can just choose random times uniformly. Yeah.
Thank you so much. Thank you so much.
Any more question?
But if you want to discuss this point, I mean, it's a little bit tricky and also counterintuitive. So if you want to discuss this point, I'm happy to discuss it.
Okay, so in case of no question, let's thank Thomas again.
Thanks.